We are now going to extend our knowledge of ions by looking at those ions which can make more than one charge. So let's look at a few examples. Copper. Copper can make a +1 charge or a 2+ charge. And each of those ions has to get their own name. And so they are named copper 1 and copper 2. This is much nicer than in the old days when we actually had to give them Latin names. This was called cupric ion and this was called cuprous ion. So this is how we do it now. Iron produces an iron 2 ion and an iron 3 ion. So you'll notice how we put these in Roman numerals in parentheses. And lead makes a lead 2 ion and a lead 4 ion. There is no lead 3 ion. So you can see we can't easily predict the patterns in terms of which charges these ions will make. So the way we name ionic compounds is actually quite simple. We say the name of the first element, the cation, and then we simply say the name of the second element, the anion. And then we change the ending of the name of the anion to IDE. If the first element is able to make more than one charge, we must include that within the name. And so we will put Roman numerals in parentheses right after that name of that element. Important to know, Roman numerals only show up in names. You will never see a Roman numeral in a formula. So let's practice with this. So we say the name of the first element, which is simply magnesium. And then the name of the second element is chlorine, but we change that ending to "ide", so it's magnesium chloride. Is that it? Well, can magnesium form an ion with more than one charge? And the answer to that is no. Magnesium is in group 2. It's always +2 charge, so its name is magnesium chloride. I would consider magnesium 2 chloride to be incorrect. This is just how the name is. It is also not magnesium dichloride. We'll talk about when we use prefixes later, but this is the name, magnesium chloride. Let's try another example. How do we name this compound right here? Well, it's very similar to what we just did. We have copper, and then chlorine, we changed the ending of its name. So far we have copper chloride. Can copper form an ion with more than one charge? So you're not supposed to memorize all the ions that can have more than one charge. You just have to know which ones only have one charge. So it's not in group, copper is not in group 1, not in group 2, and wasn't any of the other 4 special cases, which were aluminum, zinc, silver, and cadmium. So yes, it can form more than one charge, and we have to include that in the name. So the correct name is copper 2 chloride. You might be wondering where I got the 2. It's very important that you learn the logic behind this. It turns out that we know the anion can only make one charge. This is always how we're going to solve these kinds of issues. Chloride always has a 1- charge. We have 2 chlorides in the formula, Cl2. So that means there's a total of 2-. Remember the very important rule. The total charge of all ionic compounds has to add up to 0. So if the chlorides add up to -2, the positives have to add up to +2. And so that means that the one single copper ion must be 2+. And so this is copper 2 chloride. You want to be able to practice with this logic and solving this for compounds. This can be challenging, but once you've done it a few times, you won't find it very difficult. To just show you some examples of differences, if we look here at copper 1 oxide versus copper 2 oxide, you'll notice that they look distinctly different. And it turns out they have totally different properties. Here is an example of iron 2 chloride versus iron 3 chloride. You can see that they clearly look different. And although you can't see it here, they definitely have different properties. So what I would like you to do here is write down the formula for all of these ionic compounds and try to attempt to name them. Remember the procedure. You say the name of the cation and then the name of the anion, changing the ending to IDE. You ask yourself, can the cation make more than one charge? If it can, you have to include that as part of the name. So I'd like you to please pause the video. If you get stuck, you can unpause it to look at the first few. And when you're ready, I'm going to go through these each in order. Okay, I'm assuming you've unpaused at this point after completing these. Alright, so what is this? So we have potassium, and bromine becomes bromide. So it's potassium bromide. Potassium is in group 1A, so it's always +1. So the name is potassium bromide. Here we have aluminum with chlorine, that becomes chloride. So aluminum chloride. Aluminum in group 3 is always +3. So we don't include the charge of aluminum in the name. So aluminum chloride. Here we have cobalt with fluorine, which becomes fluoride. So cobalt fluoride. Can cobalt make more than one charge? Well, cobalt doesn't fall into any of those categories that we talked about. It's not in group 1, not in group 2, wasn't in group 3 at the top, and wasn't one of those special 3. So therefore we must include the charge. We find the charge by looking at the anion. Fluorine is in group 7, so it's always going to have a 1- charge. There are 2 of them, so that means we have a -2 charge from the fluorines. There is only 1 cobalt, so it must be +2 to cancel out the -2 charges of the fluorine. So the name of this compound is cobalt-2 fluoride. Notice the kind of odd spelling with fluorines, fluoride. The next compound has silver and oxygen. Silver, we recall, only makes 1 charge. It was one of the special ones. It's always +1, so we don't put the charge in the name. And then oxygen becomes oxide. So silver oxide. Here we have barium, and we have nitrogen, and that's going to become nitride, IDE. Barium can only form 1 charge because it's in group 2A, so the name is barium nitride. Here we have tin. Let's just kind of skip ahead here. We know that tin is not in any of the special categories, so tin can make more than 1 possible charge. So we're going to have to say what the charge of it is here. The chlorine, as chloride here, is always -1 because it's in group 7. There are 4 of them. So if there's 4 times -1, that means the negative charge is -4. We must cancel that out with +4. Since there's only 1 tin atom, it would have to be +4. So the name of this is tin-4 chloride. This is probably the trickiest one for most students when they're first doing this. Chromium can make more than 1 charge. It doesn't occur in any of the fancy groups. So we look at the oxygens. There are 3 of these. They are oxide. Oxygen is in group 6. That means it's going to make a 2- charge ion. So 3 times -2 means that it's -6. There are 2 chromiums, and they have to add up to +6. So what would they have to be? Well, +6 divided by 2 each one of them would have to be positive 3. So we've got 2 times positive 3 is positive 6, and 3 times negative 2 is negative 6. So this is chromium 3 oxide. Finally, we have zinc with sulfur. Zinc was one of the special atoms that is always going to have a constant charge. It's always +2, so we don't need to say that in the name. And sulfur becomes sulfide, so this is zinc sulfide. Now we're going to extend this a bit further. We're going to now add to this what we call the polyatomic ions. So polyatomic ions are molecules that have gained or lost electrons at some point. Since they are molecules, we're going to find out that these whole structures are actually held together by covalent bonds, and we will talk about covalent bonds in a moment. And usually the covalent bonds are between nonmetals. There are a few exceptions to this, but most of the ones that we're going to look at, and certainly the ones that you're going to be required to know, only have nonmetals in them. So this ion here, for example, is going to have 1 nitrogen and 3 oxygens, but this whole thing is -1 charged. So this doesn't mean the oxygen is -1, the whole thing is -1. Also be careful, the 3 belongs to the oxygens. There's 3 oxygens. It's not affiliated with the minus sign, which is a superscript. Here we have a chlorine and 4 oxygens. That's a polyatomic ion, and the whole thing is -1. And here we have a nitrogen with 4 hydrogens, and it's +1. So as I mentioned, there are some polyatomic ions that have metals which are able to covalently bond, and we will encounter these a few times in lab. This ion in particular, called the permanganate ion, has a very, very deep purple hue, and we will use that to our advantage in a couple experiments. So the first polyatomic ion you need to know is going to be the only one which is positively charged, and that is the ammonium ion. So NH4 plus is the only common polyatomic cation. There are others which exist, but they're rather rare. So you need to know the common polyatomic ions by memory, and even more important, you need to be able to recognize them as a unit. In other words, when you see this, you need to not see nitrogen and 4 hydrogens. You need to see ammonium. That whole group of atoms is together. So these are the other polyatomic ions to memorize. So you already had ammonium, and these are the others. So hydroxide, which has 2 atoms, OH minus, and remember the minus is shared over these 2 atoms. Nitrate, which is NO3 minus. Acetate, C2H3O2 minus. Bicarbonate, HCO3 minus. This one is also sometimes called hydrogen carbonate, because you'll notice the ion you need to know over here is called carbonate. So that's either bicarbonate or hydrogen carbonate. You'll notice that I've arranged these in order of increasing negative charge. So these first 4 have a -1 charge. So carbonate, CO3 2 minus, sulfate is SO4 2 minus, and the only one with a 3 minus charge you need to know is phosphate. Now this list is by no means complete. There are many, many others. And in one of the dry labs you'll have to do, experiment 6, you'll use some of those others, but you can look those up in tables. You need to memorize these particular ones. And even if you're taking an exam with open book and open notes, you have to know these, because otherwise you will end up losing valuable time if you're constantly trying to look them up because you didn't memorize them. One bad piece of news, and that is there's no shortcuts on these guys. I once did learn a shortcut, and the shortcut was so complicated that it just makes more sense to make flashcards and memorize them. And bear in mind, there are many, many, many others, so we've kind of lucked out because we don't need to learn all the others. So how do we name compounds that have polyatomic ions? Well, you follow the exact same rules that you did for the other ionic compounds. So you just put the name of the cation first and then the name of the anion. Now, something new does come up here. When you need to have 2 or more of a polyatomic ion, you can't just put a 2 or a 3 at the end. Let's see if we can think about why. Well, if you put a 2 at the end here, it would no longer be SO4, it would be SO42. That would be a definite problem. You would be changing the way it works. So whenever you need 2 or more of the polyatomic ions in a formula, you put them in parentheses, and then you put the number outside. So I need you to know this. Only polyatomic ions will ever be in parentheses. You won't ever have a single atom by itself in parentheses. Also, whenever there are parentheses, there always must be a number, 2 or greater, after them. So that's what I just went through right there, the only circumstance for using parentheses in formulas. So let's look at some examples here. Here is one where we need 2 of the sodiums, and this is a sulfate. Here's an example where we needed parentheses. Why? Well, calcium always forms a 2+ charge. Nitrate is a -1 charge. So to cancel out the +2, we need 2 of these here. So by putting the 2 outside, that multiplies all of this. Otherwise, it would just be NO32. Here's another formula where I need to have 2 of these hydroxides to cancel out the charge of magnesium. Sulfur we know is 2-, and this ion is +1, so we'd need 2 of them. And we don't need parentheses here. Alright, so let's practice naming these right here. So first of all, we've got sodium. Sodium doesn't make more than 1 charge, so the name is going to be sodium. And SO4, well, go back and look. It was SO4 2-, was sulfate. So hopefully you've written those down so you can refer to those. If not, you will want to go back in the video and write down those ions. So sodium sulfate. Here we have calcium. Calcium can only make 1 charge. It's always +2. And NO3, you'll recall, was nitrate. So the name here is calcium nitrate. Magnesium can only make 1 charge, so it's going to begin with magnesium, and this is hydroxide, magnesium hydroxide. Here is our only cation that we had to know that's a polyatomic ion. Its name was ammonium, not to be confused with ammonia, which we'll talk about later. So this is ammonium. Now be very careful here. Sulfate? No. Remember, when it's the element by itself, its ending is "ide." So ammonium sulfide. So this is one big source of errors for students. You'll notice the 8s, all the ones with 8s on them, are polyatomic ions. The only "ide," which is a polyatomic ion, is hydroxide. There's also cyanide, but that's not on the list you had to memorize. Iron. Iron makes more than 1 charge, so we're going to need to figure out the charge of that. And we figure it out from this guy. So this is not phosphorus and 4 oxygens, it's phosphate. Phosphate is -3 charged. So therefore, this iron would have to be +3 charged to cancel out phosphate's negative charge. So the name is iron 3 phosphate. Now we're going to get into some of the properties and the structure of these ionic compounds. So it turns out that all the ionic compounds that we are going to encounter in this class, they are always found as solids at room temperature. And what this tells us is something very important. It means that the ions are very strongly bound to each other. They're very difficult to separate. They don't flow. Otherwise, this would be more of a liquid at room temperature, and it's not fluid. So these have all very high melting points, as I mentioned earlier. In ionic compounds, we find that the ions come together in very well-organized patterns at that submicroscopic level. And these patterns all have special names like body-centered cubic and face-centered cubic and hexagonal close-packed, but we don't have to worry about any of those names. You just have to know that they come in very nice either cubic or hexagonal shapes. And so we could see an example of this by looking at sodium chloride, if we could look at it from a submicroscopic level. So this comes from a textbook we used to use. So we're going to talk here about how we might form an ionic compound. So here we have a weird representation, or it's kind of a classical figure, of a sodium atom. And here we have a chlorine atom. Remember, the electrons don't really rotate in orbits like here. That's just a nice fancy picture. Sodium was a metal. It wants to lose a valence electron. Chlorine wants to gain it. So what happens after this is done? Sodium is now +1. Chlorine is now -1. For reasons, we're not going to go into this in this class, but you'll notice also there was a change in size, and that's fine. Positive ions are always smaller than their parents, and negative ions are always larger, but you don't need to memorize that. And then what happens? Well, the sodium is now positive, the chlorine is now negative. They're very strongly attracted to each other. But this didn't happen just one atom at a time. There were millions and millions of atoms probably doing this at the same time. So this chlorine, which is negative, isn't just going to be attracted to one sodium. It's going to have lots of sodiums surrounding it. And then those sodiums, in turn, are going to be surrounded by lots of chlorides. So ultimately what we get is a structure that looks like this. This is what we would call a crystal lattice. You don't need to know that name for right now. And this is only part of the structure. This pattern would continue going, not to infinity, but it would go out maybe millions and millions of atoms. So whereas we have here this pattern of chloride, sodium, chloride, you'll see the pattern changes to sodium, chloride, sodium, and then the pattern starts to repeat. Chloride, sodium, chloride, and then over here you would have another sodium, chloride, sodium, and this would just keep going out in 3 dimensions. So the important thing to understand here with these ionic compounds is we don't have what we call molecules with ionic compounds. A molecule would mean that these two atoms are together and that's it. And it would also mean they're sharing electrons. That does not happen in ionic compounds. They do not very well share their electrons. The electrons got moved and that's the end of it. And also, we will notice here that they don't form just pairs of atoms. They form large, complicated lattices. I'm going to go ahead and end this video here, and we'll come back and talk about covalent bonding in the next video and molecules. Thank you.